Hi everyone, this is Mrs. J, and today we're going to do a little bit of right triangle trigonometry review. Alright, I have a quick warm up for you guys, so pause the video and give it a try. Alright, so hopefully you've heard the phrase SOHCAHTOA before. If not, that's okay. It's just a mnemonic device that we use to help us remember what our three basic trig functions represent. So it stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, so we're going to start by reviewing our 6 basic trigonometric ratios, which are sine, cosine, tangent, cosecant, secant, and cotangent. So sine, cosine, and tangent are the ratios that are covered in SOHCAHTOA. So sine is opposite over hypotenuse, and then just so you guys know, O is going to stand for opposite, A is going to stand for adjacent, and H is going to stand for hypotenuse. So you could describe the sine of any angle by taking the opposite side over the hypotenuse. And I do want to remind you that the hypotenuse is always opposite the 90-degree angle. It should also always be the longest side in your right triangle. So for cosine, you take the adjacent side, which means the side next to it, and it's over the hypotenuse. And tangent is the opposite length over the adjacent length. Now, cosecant, secant, and cotangent are what we would call the reciprocal ratios. So cosecant is actually the reciprocal of sine. So you just take the ratio of sine and you flip it. So it's actually hypotenuse over opposite. And then secant is the reciprocal of cosine. So instead of adjacent over hypotenuse, it's hypotenuse over adjacent. And cotangent is the reciprocal ratio of tangent. So it's adjacent over opposite. And I remember this, especially the first two. I always remember that the cos don't go together. So cosine and cosecant are not reciprocal. So sine and cosecant, cosine and secant, and then tangent and cotangent. So if we want to describe the sine, cosine, tangent, cosecant, secant, and cotangent of angle A of this triangle, we can do that. One thing to point out, although we write this as, it looks like it says sin, right? This is the shorthand for sine. We should always read this sine. Same for this one. Let's not read it as cos or cos. Let's actually read this as cosine. Let's read this as tangent, cosecant, secant, and cotangent. So say the full word. So we're doing the sine of angle A. So we find angle A, and it does matter which angle we're working with here because it would change what is opposite and what is adjacent. So if I'm doing sine, again, it's opposite over hypotenuse. So the side opposite angle A is side A, lowercase a, and the hypotenuse is C. And just basics in geometry, hopefully you remember that when you're naming parts of a triangle, the angles are always going to be capital letters, and the sides are always going to be the lowercase letter that corresponds with the the opposite angle. So notice angle A and side A are opposite each other. And if you want to describe the ratio for the cosine of angle A, again, it's the adjacent side, which is B, over the hypotenuse, which is C, so B over C. And the tangent is the opposite side over the adjacent side, so A over B. Now we're still working with angle A, but this time we want to do cosecant, which remember is hypotenuse over opposite. So the hypotenuse is C, the opposite is A. So it's C over A, and you'll see that that's the reciprocal of our answer from the sine. And then secant is hypotenuse over adjacent, so C over B. Again, the reciprocal of our cosine ratio. And then the cotangent will be adjacent over opposite, so B over A. And there you have it. So that's how we can use our 6 basic trigonometric ratios. So now that we've reviewed that, we're going to work with some numbers instead of just variables. So we're going to find all 6 trigonometric ratios of angle D. So one thing you might notice is that we are missing a side length. So another quick reminder, anytime you have a right triangle and you're missing a side length, if you have two of the sides, we can use the Pythagorean theorem. So this is a good little review of that as well. So remember, the Pythagorean theorem states that a squared plus b squared equals c squared, where c is our hypotenuse. So we can say 12 squared plus b squared, or you could use whatever variable you want, equals 13 squared. So b squared is going to be 13 squared minus 12 squared. So this is actually what we call a Pythagorean triple, because when we actually solve for it, we get a whole number. So 5, 12, 13 is a really common thing you'll see with right triangles, because there's only so many triples that work where all three side lengths of a right triangle are just nice whole numbers. So we call this a Pythagorean triple. Another really common one that you might know is a 3, 4, 5, because 9 plus 16 is 25. So we call this a Pythagorean triple. All right, so now that we know all of the side lengths, we can start listing our ratios. So we'll start with the sine of angle D. So it's opposite over hypotenuse, 5 over 13. The cosine of angle D is 12 over 13. The tangent of angle D is 5 over 12, opposite over adjacent. The cosecant of angle D should be 13 over 5, the reciprocal of sine, or say hypotenuse over adjacent or over opposite. The secant of angle D should be the reciprocal of cosine, and the cotangent of angle D should be the reciprocal of tangent. So there's our 6 trigonometric ratios. Okay, so now we're going to still be working with our trigonometric ratios, but we're going to be solving the right triangle below. So anytime you see the directions say to solve the right triangle below, it just means find all of the missing sides and angles. So one thing we can find right off the bat, you don't have to do it in this order, but you'll see that we know 2 of the angles. So remember, this means a 90, and then we know that angle A is 36. So hopefully you remember that the sum of the 3 angles of a triangle is 180. So we can say that angle B is just 180 degrees minus 36 degrees minus 90 degrees. So we don't have to start by doing this, but I think it's an easy thing to start with. So we can see that angle B is just 54 degrees. So I can label that in it, or I can just box it here. So now we need to go about finding some of the missing side lengths. So there's 2 legs that are missing. So here you can see we can't do Pythagorean theorem because to do Pythagorean theorem we need to know at least 2 of the sides. However, we can use one of our trig ratios to help us find either A or B. And there's actually a lot of different ways we can go about this. So let's say you want to use angle A. We could say that the sine of 36 degrees is opposite over hypotenuse. So we could say A over 10. And then we can solve in this way. So we'd multiply both sides by 10. So 10 times the sine of 36 degrees. And then this is something that you would plug into your calculator. It is important to make sure that your calculator is in degrees and not radians, which is a different measurement for angles. And you'll get A is approximately, I'll just round to the nearest tenth, 5.9. So that's one way you can solve for A. But you could actually also solve for A using angle B. We could have said the cosine of 54 degrees. And if I want to solve for A, we would actually use cosine because it's adjacent over hypotenuse. So A over 10. So A equals 10 times the cosine of 54 degrees. Or again, if you plug this into your calculator, and you get a decimal approximation, you get the same exact answer. So again, you don't need to do both. This is just 2 different ways that you could solve for angle A. So once we know that this is about 5.9, a few different ways we can go about this. Now we could do Pythagorean theorem to help us find side B, or we could use another trig ratio. We have even more options now because we could use either angle, and we could use sine, cosine, or tangent depending on which angle you're working with. So let's say we're going back to angle A. Angle A. So we could say that the cosine of 36 degrees would be B over 10, adjacent over hypotenuse. So angle B is 10 times the cosine of 36 degrees. So again, you could just plug this into your calculator, and you should get about 8.1. Again, that's not the only way we could do this. We could also have said that the sine of 54 degrees is B over 10 because sine is opposite over hypotenuse. So if you plug this into your calculator, you should get the same answer as if you were using this scenario. And for this one, we could even use tangent. We could say the tangent of 36 degrees is equal to 5.9 over B. And if we do this, we would multiply both sides by B and then divide both sides by tangent. So you get actually 5.9 divided by the tangent of 36 degrees. Or if you wanted yet another way to find side length B, you could say the tangent of 54 degrees, so now we're using this angle, would be B over 5.9. So B is 5.9 times the tangent of 54 degrees. In all of these scenarios, you would get about this same answer of roughly 8.1. So there's a lot of different ways you can solve these problems. I would say in terms of rounding, if we're going to be using tangent, we're using a value that we found and that we rounded. So if you can find a way to use values from the original problem, you'll probably get a more accurate answer. But really, it's okay to do this. Or again, a last way we could have found side length B is using Pythagorean theorem. So we could have said B squared plus 5.9 squared equals 10 squared. So B would just be the square root of 10 squared minus 5.9 squared. Again, you should get approximately 8.1. So there are a lot of different ways once you get started to finish solving these right triangles. Now we're going to move on to a different scenario. So what if you want to find the angle instead of the side length? So what if the angle is something that you're missing and you need to find? In that case, we would use our inverse trigonometric functions, which are arc sine, which we write like this, arc cosine, which we write like this, and arc tangent, which we write like this. So remember, when you see something to the power of -1 in this context, like a function to the power of -1, it's the notation that we use for an inverse function. And when you see this, I'd like you to read this as arc sine, I'd like you to read this as arc cosine, and I'd like you to read this as arc tangent. So remember, when you're working with just one of your original trig functions, like the sine of theta equals x, our input right here is an angle, and then our output is some value. Right, when we set up our trig ratios, we would say like the sine of 36 degrees equals some value. But with our inverse trig functions, our input is now some value, and the output is an angle. Because remember, for inverse functions, the input and the output are swapped. So again, if you are trying to find the angle, given some side lengths or given a ratio, that's when we're going to be using our inverse trig function. So just remember, for basic trig functions, our input is an angle, our output's a value, and for inverse, our input's a value, our output is an angle. So let's look at this next example where we will need to use our inverse trig functions to help us solve this right triangle. So again, we can start by finding this missing side length. We have 2 of the sides of a right triangle. So we could say 14 squared plus, I'm going to call this lowercase a because it's opposite angle A. So a squared equals 21 squared. So A is going to equal the square root of 21 squared minus 14 squared. So side length A is going to be approximately 15.7. All right, so now that we've found all the sides, we need to start finding our missing angles. So here, since we only know one of the angles, we can't use that the sum is 180. So what you can do is you can look and say, let me set up one of my trig ratios. So let's say we're trying to find angle A. We could say, okay, the sine of angle A is the opposite over the hypotenuse. So 15.7 over 21. Remember, the hypotenuse is always opposite your 90-degree angle. And again, since in this case I'm trying to find the angle, I need to use the inverse trig function. So I'm going to swap the input and the output. So we'd say the arc sine of 15.7 over 21 will equal angle A. So this we're going to need to plug into our calculator to get a decimal approximation. And just so you guys know, the arc sine button is directly above your sine button on most scientific calculators. So here we should get approximately 48.4 degrees. So remember, it is the angle, so we need to have the correct units. And again, this isn't the only way we could have found angle A. We could have used arc cosine or arc sine. So we could have said the cosine of A is 14 over 21. So A is the arc cosine of 14 over 21. Or we could have even used tangent. So we could have said that the tangent of angle A is 15.7 over 14. So A is the arc tangent of 15.7 over 14. And whichever one you use, you should get the same value as your angle, so the same answer. So now that we know one of the angles, we could use that the sum of the three angles needs to be 180. So we could do 180 minus 48.4 minus 90 equals angle B. So angle B should be 41.6. I think this is the best way to go, especially in terms of rounding. You do want to make sure above anything else that your three angles add up to 180. So maybe you use an inverse function, and if you round, maybe you get 41.7. That wouldn't make sense because your angles, they have to add up to 180. So I'd say once you find one of your angles, do the angle sum to find the last angle. However, maybe just to see and just for extra practice, we could have found angle B first using any of our inverse trig functions. So let's say we set up, I don't know, the sine of angle B is 14 over 21. So angle B would be the arc sine of 14 over 21. So plug this into your calculator just to see if we got the same answer. And you get here, actually, if you round, it's about 41.8. So you could see that the rounding could become an issue with this. So it's very close, but again, once you find one angle, find that and round it, and then do the angle sum to find the last one. But you can see we'll get about the same answer either way. And it doesn't, I guess I would accept multiple answers for this depending on what angle you started with. But again, there's lots of different ways, paths you could take for these types of problems. Whichever you use, as long as you're showing your work, is totally fine with me. All right, the last concept we're going to review today is the concept of special right triangles. So there are two special right triangles that you definitely need to commit to your memory. The first one is right here. I call it, or most people call it, a 45, 45, 90 triangle because the three angles are 45, 45, and 90. And the second one is a 30, 60, 90 triangle. So these two triangles are special because the ratios of their three side lengths are always going to be the same. So for a 45, 45, 90, the hypotenuse is always going to be exactly square root of 2 times as long as either leg. And remember, this is why it's called an isosceles right triangle. When the two angles here are the same, the opposite sides are also going to be the same. And when two legs of a triangle are the same, we call it an isosceles triangle. So again, this ratio, the hypotenuse is always going to be exactly root 2 times as long as either leg. And for a 30, 60, 90, the hypotenuse is always going to be twice as long as the shorter leg. The shorter leg should always be across from the smaller angle. So that's another concept from geometry. The side lengths they correspond with the size of the angle. So the smallest angle is always opposite the smallest or the shortest side length, and the largest angle, which is 90, is always opposite the longest. So the middle angle should be opposite the middle side length. So again, this ratio, the hypotenuse is always double the shorter side length, and the other leg is always exactly root 3 times your shorter side length. So anytime you have one of these special right triangles, you should be able to find any of the missing parts without a calculator, so by hand and given exact values. So what I like to do is I like to actually draw my own next to it, and I like to create a ratio that we can do because we have similar triangles. So I'll show you guys how to go about that process. Okay, let's look at the first part of example 4. So we're going to find the missing parts. So here we have a 45, 45, 90. So like I said, I like to draw my own triangle, and I like to try to make it the same orientation. So I try to draw the angles kind of in the same location. And then I mark it up with our starting ratios, 1, 1, root 2. So these are similar triangles. Similar triangles are two triangles that have the same 3 angles, different side lengths, but if you have similar triangles, their side lengths are proportional. So I can set up a ratio. So I can see that I have my hypotenuse, so I can say 5 over, and then I'll match it with the hypotenuse of this over root 2. And let's say I'm trying to find this side length first, equals x, and I say which side length corresponds with this? Oh, 1. And then you could cross multiply. In this case, you don't need to. It's just x equals 5 over root 2, which remember, if you rationalize, should be 5 root 2 over 2. So this side length is 5 root 2 over 2, and since it's a 45, 45, 90, so is this side length. So we found all of the missing parts. So again, I like to draw my own triangle and set up a ratio because they are similar triangles. All right, for part B, you can see that we have a 30, 60, 90 triangle. So again, I like to draw my own, and I like to try to make it the same orientation. So something like this. Here's my 30, here's my 60. So I know the leg that's opposite the 30 is 1, the hypotenuse is 2, and the last leg is root 3. So I can set up my proportion because they are similar triangles. So I see that 15 and root 3 are like in the same relative position. So we can say 15 over root 3. And let's say I want to solve for x first. Well, I see that x and 2 are in the same relative position. So I can say equals x over 2. So I multiply both sides by 2. And then I rationalize. So I get 30 root 3 over 3. So x is 10 root 3. And then once I know this, well, I know that the shorter leg is always half of the length of the hypotenuse. So we could say, okay, y is going to be 5 root 3, but we could also set up a ratio to solve for y. So I'm going to use my same 2 starting points, 15 over root 3 equals y over 1. So y is just 15 over root 3, and if you rationalize, you get 5 root 3, which again is what we should expect because the shorter leg should always be exactly half of whatever the length of your hypotenuse is. So again, anytime you are working with a special right triangle, a 30-60-90, or a 45-45-90, I would absolutely expect you to be able to solve it without using a calculator and by providing me exact answers. Okay, that is all for today's video. Thank you so much for watching.